Yeah, good. So we're back on air. Okay, so now what are we going to do with this? What people did with this? Well, we are going to see that in a second, but there are some very general cognitive questions that people asked. Like, for instance, how specific is the information about the speech compared to other sounds, right? So our cognitive system is good at recognizing different sounds, but it's super good at recognizing the speech of the people. So we think that speech has something special, right? How much? How special? So remember Wernicke, remember there is a whole part of our brain which, if it's damaged, we really have problem in converting the sounds into basically phonological representations of words, right? So very specific. We think that the speech processing is very specific, and another question is how independent is the speech processing from a general acoustic processing, right? Do we have certain areas of our brain who do some specific work in order to decode speech, or the same area that processes the information about, I don't know, this sound like slapping on the table or the sound of the wind is the same area that processes the information of the speech? What is your guess? And who knows about this answer? So probably Alice, please don't say anything, okay? What is your guess? Is there an area, a specific area in the brain that processes the speech or not?
My guess is yes.
Right. Since we know that our brain is so specialized, the different parts of our brain are so functionally specialized, it's a kind of a good guess, right? So another relative question is, at which level can the comprehension be impaired? So if we have specialized areas, we would predict that we can have a selective specific impairment, for instance, of our ability to perceive acoustic sounds, our ability to perceive phonemes, and our ability to retrieve words. That each one of these single specific skills can be selectively impaired. Okay? And this is exactly what people asked. But then again, let's say that we have this area which processes sound, this area which processes speaks, this area which processes whatever, wind, position, localization of sound. How is the processing flow? How is this like a cascade processing flow where you have a primary processing and then more advanced processing, or everything happens in the real time, and in technical terms, everything happens in parallel? Okay? So for instance, Puppel, who is a famous neuroscientist of speech, compared two different possible models, okay? The model here assumes that you have an early hearing capacity, and then on the where path, you are actually processing the localization of the sound. On the what path, you have a primary auditory pattern recognition, the first analysis of the sound of general purpose, and then on top of that, you do a specific analysis for the speech, right? This would be a cascade model, because you see there is a flow on the information processing that goes from hearing to more high advanced processing to speech processing, okay? But as far as we know, could be like this. It could be that you have a very first early hearing capacity, and then you have parallel processing of speech and of other auditory patterns that are not necessarily speech, okay? So we have these two different options, these two different hypotheses, and we want to see which one of these is true. How do we do that? For instance, we can look at neuropsychological problems, at neuropsychological damage, okay? For instance, we know that there is a syndrome called auditory agnosia. So agnosia, it means that when you cannot recognize something, right? From the Latin word, I think gnosco or gnoseo, something like this. And so if we know that you cannot recognize sounds, right? For instance, the sound of the coffee maker from the sound of the broom cleaning the floor. Now, if your speech perception is dependent on this first sound processing capacity, if you have auditory agnosia, there is no way you can process speech. If these capacities are actually parallel and independent to each other, at least to some degree, then even if you suffer from auditory agnosia, even if you cannot recognize the sound of your car, you can still comprehend speech. Do you see this question? Good. So what is the answer? The answer, right, so, sorry, prediction, yeah, what I said, according to this model, if you have auditory agnosia, you shouldn't be able to process speech. Whereas here, speech comprehension should be preserved, okay? The reality, guess what? Meet pure word deafness. So pure word deafness is a syndrome according to which you cannot comprehend speech, you cannot repeat speech, you cannot recognize word, but you can recognize music, you can recognize familiar non-speech sounds like your dog barking, and you can hear, basically, right? If you have auditory agnosia, you can hear, you can understand speech a little bit, you can repeat speech that you hear, but you cannot recognize familiar sounds. So this is called double dissociation, and is the most beautiful kind of pattern you can find in neurophysiological data to show you that two different skills, two different capacities are relatively independent one from each other, okay? And then you can have cortical deafness. If you have cortical deafness, your auditory cortex doesn't work, so some low-level speech processing, which is important for both capacities of recognizing familiar sounds and recognizing speech, is not gonna work, okay? Still, for instance, your cochlea would be working, your thalamus probably would be working. You might have some very, very low level reaction to sound, like turn your head to a strong sound, but you're completely deaf. You don't hear anything, okay? So yeah, so this dissociation shows us something interesting, that speech processing is quite particular, it's quite specific.
Can I ask a question?
Please.
Can that change or evolve? Like, can you regain, I don't know, recognition of music at some point?
So, I mean, the simple answer is I have no idea.
Okay.
Because I'm not, no, I mean, like, I'm not.
That's fair enough.
No, I have no idea in particular about this kind of syndrome, right? But I would expect that, yes, of course, you might have some extent of recovery, right?
I mean, there is the cochlear implant for kids who are born deaf. So
All right.
I don't know if that's like connected to that kind of deafness, but.
All right. So this is a very interesting question, and it prompts me to tell you a little bit more, right, about the kind of deficit that you can have. So in your system, you can have some sort of peripheral deficits, like your cochlea doesn't work very well, right? Or some higher level deficit, like your primary auditory cortex is damaged. If your primary auditory cortex is damaged, then you have cortical deafness. That's why it's called cortical deafness, right?
Yeah, sure.
But if you need a cochlear implant, it is because you have a peripheral problem. So, for instance, your middle ear is damaged. The little three bones, the staples, and the other two that I don't remember the name in English, in Italian, staffa, incudine, martello, the little hammer. If these bones, for instance, are broken, right, you're going to be deaf, because there is no way you're going to be able to convert the sound from the variation depression of the air to your perception of sound. But Here comes technology. I'm gonna put your cochlear implant in your ear, right? And what the cochlear implant does is exactly what your cochlea does. So it converts frequencies into electric signal, and it will stimulate directly your cochlea. So it will trigger an electric reaction into your cochlea that then will send the signal to your brain, and you will start hearing again. Of course, at the level of our technology, cochlear implants are limited to just a few tones. So you have to reprocess the real perception of sounds into just a few tones, right? But already with that, you can already have a lot of information, and you can even understand speech, okay? So that would be the solution to a peripheral problem, assuming that your acoustic cortex, your hearing cortex is intact. But if your hearing cortex is intact, is damaged, sorry, then there is no way that you can recover the ability of hearing unless some other parts of the brain are gonna start doing the job that your hearing cortex was doing, okay? This is called functional recovery or functional takeover, and it's due to what we define brain plasticity. So our brain is very good at trying to substitute a damaged part of your brain that doesn't work with another part of the brain that is going to do the same function as the previous part, okay? Unfortunately, this recovery is limited. So if your lesion is too extended, or if your whole auditory cortex is damaged, your chance to recover the ability is going to be very low. But if your damage is a little bit, is not that extended, right? Then chances are that you will not hear anything for a few days or weeks, and then you will start recovering your hearing capacity because your hearing cortex will start working again, especially helped by other parts of the brain. Did this address your question?
Yeah, perfect. Thanks.
Thank you very much. Okay, so you know it's an interesting and complex system made of different parts, of different components that are highly functional specialized. Okay. Now, then we can have some more questions like, what is the level of encapsulation of this component? Are they modules? Do they work autonomously, independently, or they work interacting with other components? Okay. And these are the kind of questions that neuroscientists asked while studying this phenomenon. And then we come to one of the most famous work on these things by Scott et al. From 2000, okay? And this is the first study that we are gonna discuss. So the name is Identification of a Pathway for Intelligible Speech in the Left Temporal Lobe, okay? So the starting point is that we know that we have a strong dominance of your left hemisphere for language, but in a lot of studies, you found bilateral activation by speech in healthy individuals. So you find that both your hemispheres are active, especially in the temporal regions, okay? In your temporal lobes. And then, you know, what they said is like, maybe we never managed to find a specific activation of the left hemisphere because our baseline was not really nice, right? This kind of reminds about Alice's question about the word recognition that we talked about last time. So it's very important that your baseline is pure enough, because when you're going to subtract your baseline to your experimental condition, the pureness of your baseline is going to determine what is left in your effect in your experimental condition. So basically what they said, okay, subtracting method, and you know what it is, right? And they employed PET. PET, I haven't told you what it is. It's not fMRI. It's something kind of similar, but instead of exploiting the molecule of waters in your neurons, what it does is basically injecting in your blood some radio transmitters, and then these radio transmitters are going to emit basically radioactivity, low-level radioactivity from your blood, and this will go out and will be captured by some kind of sensor which work like an X-ray machine, basically. Okay, so you are emitting energy from your blood, and then depending on where your blood is and how much blood you're using in different parts of the brain, this is going to go out and it's going to be captured by some sensor. Okay, so it's very, I mean, for what interests to us, it's actually, you know, we could assume that this is fMRI. The reason why some people still use PET, well, once we didn't have fMRI, so it was our only option, and second, certain areas of the brain are not very easy to investigate with fMRI due to signal distortion. So sometimes it's better to use PET. Okay. All right. So what I did was like, yes, let's use a passive listening task, and let's use 4 different conditions. Okay. One condition is normal speech. The other condition is noise vocoded speech, which is a harsh whisper but comprehensible after training, which is exactly what I showed you. Okay. Noise vocoded speech. Vocoded because you're using a vocoder, which generates a new sound based on the sound that you put as input. But noise because it's using a noise generator, which does not retain the pitch properties of the incoming of the original signal. Okay, so it's like a whisper, but you can still recognize the sounds. And then you can keep on destroying the signal, and you get to a rotative speech, which preserves some phonetic features like fricatives, voiced and unvoiced, and certain intonation, but you cannot really understand the words that are being said. Okay. And then there is the worst condition, which is rotated voice no coded speech. So you apply this transformation, the rotation, to the noise vocoded speech, and then you get a sound which is completely distinct from speech and does not retain any original property of the speech. Okay. So these 2 conditions, you can understand words. These 2 conditions, no. Here you can get some information about certain structural property of the speech. Here, completely nothing. Okay. So why do you use this and not just some random noise? Because this condition will preserve some physical feature of the signal, like for instance, the amplitude of the signal, the amount of energy that is transmitted by the signal, okay? Which is basically what you take up and down when you turn your knobs in your stereo, on your stereo, okay? Right, and then you can have some contrast. So for instance, you can take all the 3 conditions and get rid of this one, and then you have basically different level of speech phonetic contrast. So what happens when you have phonological recognition, okay? Or intelligible speech contrast, where you take the intelligible conditions and you subtract the unintelligible conditions, and this should tell you what happens when you perceive intelligible speech. Intelligible means that you can recognize the words, the lexical items that are included in the speech, even though you don't know the meaning of these lexical items, okay? Like when people talk to me in German. I know they're speaking in German. I know they're using some German words, but most of the time I have no idea what they mean, okay? So we have a phonetic contrast that tells us something about what happens during speech processing without lexical access. And we had intelligibility contrast, which tells us what happens when we have word recognition, okay? And with this fine, cool methodology, what they found was this. So activation of your left superior temporal gyrus. You see, this is kind of overlapping to the belt and parabelt area that we were looking at, right? But when you have the intelligibility contrast, you move a little bit down. You move more inferior, and you get this activation of the STS, which is the superior temporal sulcus. Okay? So not only they managed to find for the first time a specific activation of the left hemisphere for speech, but in particular, they also found this this split between these areas, which is specific for speech processing, but more low-level features, okay? And this area, which is specific for speech processing with word recognition, okay? Which means that you have some lexicon in here. You have some connection between phonological representation and lexicon, whereas here is mainly phonetic processing, okay? Good, so very happy they said, we finally found evidence for the specificity of the left hemispheres for intelligible signals in passive listening. And then they talk about the anterolateral stream of neural information from the primary auditory cortex to the higher level areas, STS, STG. STS is only activated when you have word recognition. And guess what? If you look closely to the neurons, you are going to find some monosynaptic connections between your primary auditory cortex and your STS, which means that these areas are directly mapped onto your primary auditory cortex. So the sound signal does not have to take a lot of turns in order to get to this high level processing, which is basically almost immediate, okay? And this tells you something about how certain things are processed in the brain. Yes, so it was also confirmed by single cell recording in primates, okay? Primates have species-specific vocalizations, and they have certain areas of their brain which are tuned into processing this species-specific vocalization. Probably some rudiments of our language ability, okay? Is this clear? Is there any question? Okay, good. So let's move on to another experiment, which is even fancier than this one. So this is by Overath and al. And it's called the cortical analysis of speech-specific temporal structure revealed by responses to sound quilts, okay? So the idea is that speakers produce very different sounds when expressing the same utterance, right? How are we able to understand an utterance and to know that the meaning, the sentence that different people say is the same sentence, although the physical properties of their speech is completely different? Well, some sort of linguistic analysis is going to help us, preceded by a stage of lower level acoustic analysis. We have seen a little bit of that. And then we must have a mapping between this acoustic analysis and our linguistic analysis. And, you know, several layers of intermediate invariant representations like features, phonemes, a, b, t, d, and syllables, da, ba, ta, okay? Before getting to the word level. So we must have some specific processing at all these levels in order to get to the sentence level or to the word level, okay? Now, Overath et al. Start with some critics to the previous studies. So they say, you know, previous studies basically manipulated the intelligibility, both linguistically and acoustically, and we have seen an example, right? And then from this, they infer, is there a difference between acoustic and linguistic processes? Or they manipulate some speech-relevant acoustic processes, and then they ask whether there is a speech-specific mechanism, right? So they say, okay, now our study is a little bit different. It's gonna focus on the temporal attributes of speech. So a lower level with respect to the previous experiment that we have seen, okay? Or better, it's gonna focus on what is right below the phonetic processing of sound, okay? And the idea is to use foreign speech, use German to English speakers, so that they would not access the meaning of any single word, okay? Assuming that they don't speak German like me. And their goal was to isolate the auditory analysis of speech based on these temporal attributes, okay? So the fancy methodology they use is the one called scrambling methodology, okay? and they took inspiration directly from this interesting study. So by Green-Spector, 98. So what they did was to have different level of scramblings of this nice little kitten here, okay? So here you have the whole kitten. Here you just cut this cat into chunks, and you have a lot of chunks, but still you can recognize some part of the cat. Here, it is really difficult to recognize a cat, but maybe you see the nose, some grills, something, and you're like, oh yeah, that's a cat. Here it's almost impossible. And here you just see a mosaic of white and gray and black, okay? So you see the rationale. By parametrically degrading the signal, in particular a picture, I want to map this parameter to certain areas of my brain, which, if they are specific to, for instance, object recognition, then they're gonna have the same envelope. You see the rationale, right? So, and then, you know, they showed this in fMRI, and then they saw what's going on and which area would be active. Take your primary visual cortex. It's always active. Your visual cortex likes every kind of visual stimulus. Even more active when you have more scrambling, fancy things going on. Then if you go to your V4V, which is an associative, a supplementary visual cortex, then you see that you kind of see some degrading a little bit of processing the more the picture is not intelligible, right? If you go to the LO, which I'm not really sure what it is, but it must be some area which is involved in object recognition, this area is only happy when you give something in which you can see a cat. As soon as your cat chunks are too small and you cannot see that there is a cat in here, this is gonna be almost silent and completely silent, okay? So is this clear? Is this clear, the methodology that you're using? Okay. Right, so you see increasing activation, decreasing activation, and completely suppressed activation for the graded object picture. Now they're going to use exactly the same rationale, okay? But they will use quilts of sound. What is a quilt? A quilt is a speech segment whose length is varied parametrically from 30 milliseconds to 1 second. And then it is scrambled and reordered so that only the local constraints are kept. So basically, you cannot basically recognize. You know, you can recognize if it's like a kind of a speech, or if it's a kind of a sentence, or if it's like syllables, or if whatever it is, if the length of the quilt is really, 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 really short. The longer these guys are, the more you're going to be able to recognize the speech, okay? So at 1 second, you basically have, I don't know, 2 words, right? Say, John loves Mary. That's going to take 3 seconds. Then you might get Mary John loves. But if you have it like at 100 milliseconds, you're just going to hear pieces of sounds scrambled to each other. If you do that at 30 milliseconds, you're not going to probably be able to understand anything, not even that is a sentence, okay? So again, you degrade the signal by scrambling the physical properties of the signal, especially by cutting this into chunks and scrambling these chunks. The bigger these chunks are, the more information about the original signal you're going to be able to extract, okay? And then they have an hypothesis, and their hypothesis is that, you know, there are regions that are subserving speech-specific analysis, and this region should show an increasing response as the internal structure, the length of the quilt, is preserved, okay? just like with the picture of the cat. And then he said, okay, what are we going to look at? Well, we're going to look at these things called region of interest, ROI, okay? Which means that in neuroimaging, sometimes you know you have a specific area that you're interested in this case, our temporal cortex, right? And you say, okay, I want to see if in that particular point, something cool is going to happen. So they focus on a specific area of the brain. And there are different ways by which you can define these regions. So you can define them anatomically, right? You can take a brain and say, okay, this is the primary auditory cortex, and this is the planum temporale, non-primary auditory cortex, okay? A1, A2. But then you can also define them functionally. So you can look at the data and see in the data what happens, and then go to that part of the brain and investigate specifically that part of the brain, because that is the part of the brain which is mostly sensitive to the variation of your signal, okay? So they identified this area. Guess what? It's within the superior temporal sulcus, so the same area that in the previous experiment was active for intelligible sound, right? And they just analyze the contrast between the response with very long quilt and very short quilt and say, okay, the area that responds the most to this one contrast is going to be my functionally defined area. And then I'm going to zoom in this area and I'm going to see what happens with respect to all the other conditions. Okay. And here's what happened. Now, this graph shows you on the y-axis the proportion of the responses to the localizer. So the localizer is a statistical methodology to localize the activity in certain areas, right? So when it's 1, it's maximum activity. When it's 0.5, minimum activity, okay? And here you have the segment duration. 30 milliseconds, completely scrambled sound. 1 second, quite decent sound, okay? Now, let's see what happens. This is segmented speech. So German speech, scrambled, presented to English speakers. And let's have a look at primary auditory cortex and secondary auditory cortex, okay? So A1, red line, A2, blue line. What do you see? How does the primary and the secondary auditory cortex respond to the parameterization of the length of the quilt? Please tell me.
It
There
doesn't
is
seem to show
basically,
much of.
yeah,
sorry.
no difference.
Sorry? Yeah, can you say it again? Sorry, my speakers were off. Can you repeat it?
There is not a big difference.
Right. Between what?
Well, between the scrambled speech and the intelligible speech.
Right. So it's exactly your V1 for pieces of cat. Your A1 is gonna process whatever kind of sound signal you give it to it, right? But not only that, but your A2 as well. Your A2, which is supposed to do higher level computation, is also sensitive to any kind of scrambling of your original signal, right? But look at your ROI. Look at your superior temporal sulcus. Very low response when the original signal is not intelligible, to high response when you hear, when you understand that it's a speech. And intermediate responses as the length of the quilt increases, right? So this is very good evidence for the fact that this functional localizer really, really, really is sensitive to properties of the speech, okay? Now, are we done? Can we publish on Nature with this? Or we are not really sure that we can conclude what I just said? What do you think?
Would we need the double dissociation?
Right. So a double dissociation is usually a term that you use for lesional data, right? But the principle is exactly the same. So what you need to do is to use basically to have control conditions. So to take other sounds and see if this STS is going to respond the same way to other sounds. Because then if it does, it's not really specific to speech, right? So also another interesting property is that they found this plateau at 480 milliseconds. So there is no difference between scrambling stuff at half a second and scrambling them at a second, okay? Let's keep that in mind. And let's move to another control. Right, so the breezy response to short segments in STS. Specialization for processing of sound, only STS and not A1 and A2, okay? So is this really speech specificity? Or this area is sensitive to more general features of the signal? For instance, animal sounds, naturalistic sounds. Maybe the STS processes naturalistic sounds. So let's run our controls. Modulation control stimuli, right? So they synthesized some stimuli with an algorithm decomposing the speech signal using an auditory model. These would retain the amplitude modulation properties. It has a similar power spectrum, but no pitch, no prosody, okay? Something kind of similar to what we've seen before. So what did they find? Similar response in A1 and A2, you see? This is just comparing the previous graph to the new graph with the modulated conditions. This is a very short and this is a very long. Then we're just going to look at the very short 30 milliseconds and very long 1 second. And there is a very, very little variation here, a little bit of increasing signal, but nothing really, really different from before. But now look at your STS, completely silent, completely ignoring this modulation control stimuli, okay? So in this modulation control, you cannot recognize that it's a speech, okay? It's much, much worse than the noise vocoded condition that I showed you, okay? So that's good. STS is not sensitive to this. What about environmental sounds? What about animal vocalization or human action? Sawing wood, footsteps. Maybe the STS is sensitive to real sounds, okay? Same thing, same manipulation, similar response in A1 and A2 compared to the previous experiment, much, 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 much lower response in STS. Now you see a small modulation in STS, right? It's not completely flat, but it's not comparable to the great activation you had with real speech, okay? So very, very silent. Good, so the STS is not sensitive to environmental sound. Now, the litmus test. Let's take our noise vocoder, okay? Let's take our spectral voice. And you know now that the noise vocoder speech eliminates the pitch, but maintains core spectral content sufficient for phonetic identification, especially for consonants, right? So if STS is specific to processing low-level acoustic properties of speech sound, would you expect that STS is going to be active when you present noise vocoded speech or not? Guess. So we know that we can still recognize the speech in the noise vocoded speech, right? We can still recognize phonemes. So there is some level of speech recognition that should be preserved, right? So would you expect then the STS to be sensitive to this? Guess? Any guess is good. Yes, no? Who says yes? Thumbs up, who says yes? And thumbs down, sorry, and no thumbs up, who said no? Okay, I see one yes, two yes, and a lot of undecided. So I give you the solution, right? Yes, you would expect that, right? You would expect your STS to be sensitive to this manipulation because you can still recognize speech. And this is precisely the low-level speech analysis that they were interested in, with these temporal properties of speech and these things that are not sensitive to the pitch of the speech, okay? If the STS is not sensitive to this, it means that the STS is basically processing pitch, okay? What happens? Yes, very, very nice, huge modulation in both your STS and also your V1 and V2, okay? So a very similar response in A1, A2 to the previous one with some modulation, but a big, 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 big modulation in STS. So the answer is yes, the STS does not only process speech properties, but also lower level temporal properties of speech. Okay, awesome. The last experiment I did was like, okay, we noticed that there is this plateau at 480 milliseconds, right? So this could be due to the fact that some of the brain regions integrate the sound information at a time scale that goes up to half a second, some sort of syllabic level. But it could be also due to the fact that this information occurring at half a second is actually a property of the speech. So this response plateau means it doesn't increase anymore, reflects some statistical property of the speech and not some particular tuning of your cortex, okay? How can we investigate this hypothesis? Very simple, just compress your speech. Just make it twice as fast. If you make it twice as fast and you still find the same plateau, it is a property of your brain. If the plateau varies as it varies with the sound, then it's a property of the stimulus, right? And what they found is that no, it's exactly the same. You find exactly the same plateau. So this suggests that there is some particular tuning. Oh yeah, sorry. You get an overall smaller response because you were less, probably, less happy and less able to recognize that as a real speech. But the plateau is exactly the same. Okay. So this suggests, so in the conclusion, right, the STS, superior temporal sulcus, is bilaterally, not just to the left, but bilaterally tuned to the acoustic structure of speech. In particular, the temporal structures, because if you use quills to disrupt the temporal structures, you're going to have a decrease in the activity of that specific region. And that is independent of lexical and syntactic information, assuming that the English people do not access lexical information of German speech. And these results cannot be explained in terms of sensitivity to the amplitude modulation, because that was the same in all the controls, or in prosodic pitch variation, because the noise vocoded speech does not have any, noise vocoded speech does not have any prosodic pitch variation, okay? So they concluded that there's a hierarchy of selectivity whereby your primary and secondary auditory cortex responds to any acoustic stimulus, whereas the STS selectively responds for speech relevant stimuli. speech-specific analysis. So it's so they suggest there is a subsequent stages of auditory processing where you have a very, very primary processing in your primary areas and your higher level specialized associative areas, which do some specific job, especially speech analysis. And then there is a parametric sensitivity up to half a second, and then you get a plateau. Why is this? Why do we have this half a second sensitivity? We don't really know. Maybe it's due to the fact that we have syllable, words, and acoustic phonetic primitives that occur after half a second. And then our brain is tuned to capture these properties of the sounds and to capture and to represent these properties into representations that are sensitive to this timing, syllables and words, for instance. Why do they find a weak lateralization? Why do we find the bilateral effect? Maybe, taking into account the previous experiment, maybe it is really lexical access. It is really word recognition, which is critical for lateralization. And this is really interesting, okay? So these lower properties of speech are processed by both hemispheres of your brain. And then when you get to lexical access, then the left hemisphere pops up, okay? So this tells us also something about what the lateralization of language processing in the brain, when does it kick in? Probably at some sort of, from a lexical level on. It does not really kick in at the low level of speech processing, okay? Very interesting stuff. Why did they fail to identify subregions in the STS? Well, there are some limits in the spatial resolution of the hemodynamic bod response, as I told you, right? So the resolution is not high enough to find that specific regions within the STS are more sensitive to different properties. Probably if you had a more sophisticated methodology like intracranial recording or MEG, you would find difference within the STS, okay? So, is this clear? Was it clear? Is there any question, any general question? Any doubt? Okay, so now I would like you to think about certain critiques that we can move against this experiment. For instance, what are certain things that might not have been well implemented? Or what are certain conclusions that these people drew from this experiment that they were not really warranted? Do you have any thought? So, for instance, one critique that I would move immediately is that using German to test English is not ideal because they are both Germanic languages. So many words in German actually sound similarly to what they sound in English, right? So probably their speech recognition was enhanced by the fact that they were presenting words in a language that was similar to theirs, okay? Second, one of the questions is like, what exactly is STS processing? What are these speech-related representations? Is it like some kind of phonological decoding? Or is it like some, I don't know, consonants versus vowels? We cannot really know, right? Maybe it's syllables, maybe it's speech-related acoustics as statistics, maybe it's words, maybe it's just statistical regularities between words. We can't know. Phonemes, all the things above, right? We cannot go more in detail with respect to this question. And for linguists, these results are quite trivial. So you are telling me that there is an area of our brain that is analyzing speech? Wow, amazing, right? Come on, of course. There must be something in our brain doing this, right? So we must have something in our brain dedicated to processing speech-specific features to account for the existence of all these guys above. So at the linguistic level, this is not really telling us a lot, especially about the existence of these representations, right? But still, you know, neuroscientists are very skeptical, so sometimes they really want to start from the basis, and this is also kind of good to sort of pinpoint exactly the operation that certain brain networks perform. Okay, so these results are useful to convince some of neuroscientists that actually within the domain of speech, there is a strong functional specialization of our cortex. Okay. Okay, so I would not start this part, but I'm really happy about the fact that we managed to cover both these experiments. Okay, so next time we will talk a little bit about what do we mean by representations? Why do we say that our brain has representations? And how can we map issues about neuroscience, like brain activation, cortical networks and areas, anatomical properties, functional properties, to certain objects that have been postulated within the domain of linguistic theory. To start with phonemes, right? The big question in neuroscience is whether phonemes ever exist. We assume they exist in our phonology class, but are we sure that our brain really categorizes pieces of sounds in discrete phonemes? Or it's just a general sort of analysis of the sound, and you cannot really see the difference between and within your brain? It's just a continuous statistical variation of processing a certain aspect of sound, okay? So it's all about the mapping between what is on your right side and what is on your left side. And then, you know, God help us in how can we do this mapping, right? There might be multiple ways to map this stuff. For instance, one area could be specific for processing certain kind of information, or the same area could process two of these types of information at the same time. And our brain activation could react differently in different areas to these different sources of information, moving from phonology to syntax to semantics and to pragmatics. This is kind of the general picture of what we want to do in general at the neurolinguistic level and specifically in our class. Okay, so next time we are going to start with this, and we are going to try to answer this question like, is this the best way to understand how language works? To try to build bridges between neuroscientific results or neuroscientific effects and hardcore linguistic theory? Or maybe this is not actually a great idea. Maybe it's just better to think about law property of the signal and general statistical association. And maybe this is going to tell us that we've been wrong all the time when we did theoretical linguistics. And in this case, we might wondering, you know, what are we doing here if we cannot really map linguistic theory with neuroscience? At least half of the enterprise of neurolinguistic is doomed, basically, right? So we'll try to convince you that this is not the case. Yeah, so I guess we can stop here. Again, if you have any question or any comment, please, I'm all ears.
When is the next class?
All right, so the next class, I have to update
On Wednesday.
The calendar
It's on the 3rd of June.
On the 3rd of June.
Okay, thank you.
Yeah. So let me have a look at. All right. Let me also stop the recording.